Yes, Warren. So Prophese, our third finalist, has shown up event-based sensing as a paradigm shift in a holistic platform ranging from sensor to software solution. And we all know it from the nature. Event-based sensing is an alternative way of data reduction and faster reaction. There's a counterpart to limitations of traditional frame-based platforms. Please welcome Prophese with MetaVision technology. Welcome, Luca, on stage. It's yours.
Thank you very much. Thank you, everyone. Can you hear me?
Yes.
Okay, yeah, perfect. So let me share, first of all, the excitement to be part of this event in person. And second, also, my honor to be shortlisted with such a great panel of companies and people. So I would like to share with you a little bit about what we do at Prophese, in particular in the field of neuromorphic vision technologies, this new technology that we believe is going to lead the change in the way we do machine vision and AI, a technology that is fundamentally inspired by the way the human eye works. You may be familiar with the fact that actually the eye, when you look at me at this moment, your eyes are not sending an image to the brain like the same image that you are producing with your phone, but the eyes are just sending the information of what is changing, only what is moving. And this actually enabled the biological system to be extremely fast and extremely efficient. And this way, actually, the way we work in the biological system is fundamentally a way that has been optimized for many, many years, leading to biological system to be extremely efficient and fast to survive in the environment, as opposed to conventional, let's say, frame-based technologies that have been invented by us around 100 years ago, fundamentally to produce images for our leisure, for photography, for cinema. So at Prophese, essentially, we develop a vision sensor that mimic the human eye. We have engineered the most advanced event-based sensor, and we work on computer vision and AI algorithms that try to mimic also the way the human brain works. Our first silicon retina implementation has been used for, I would say, probably the most natural first implementation of this technology, which is for vision restoration of blind. So the first silicon retina has been used for retinal implants in people who have certain degeneration of the retina and unfortunately become blind. And this actually has been a great starting point for us to start then opening up many fields of applications in industrial, in IoT, in surveillance, and now also going to automotive and mobile. The company is 7 years old. I co-founded this company in Paris. We are now a little bit more than 100 engineers. We are the pioneers in this field with more than 50 patents. We raise money from financial and corporate investors such as Bosch, Renault, Nissan, Intel, and some others. And today our business model is very simple. We develop and design this vision sensor, which is a silicon retina, which mimics the biological system. And we develop the software stack to enable our partners. You see some example on the right side of the slide, to actually take this technology and build full application and embrace together with us this vision that event-based technology is going to revolutionize. So how the technology works is, let's say, I will give you a high-level explanation. So what we try to do essentially is to make pixels that are independent and asynchronous. So instead of actually producing a full image at a fixed point in time, we basically make each single pixel smart and able to react only when there is a relative change of light. But we do so by embedding some smartness at the level of the pixel itself, a level crossing sampling that is monitoring the light, and when the light goes up or down a certain relative amount, it triggers a change. So the result is what you see in the slide. So basically the sensor would react only when there is some motion in the scene, because typically this is what is creating this relative change of light, right? So for example, in this example, the background, which is static, is not being acquired over and over. That's why it appears in a white color, because there are no data produced. So three are the benefits of this sensing approach. The first one is straightforward. I mean, you see it. You produce much less data. You are not constrained anymore by a sequence of images at a fixed point in time, regardless of the fact that there has been or not a change. The second benefit is the speed of the acquisition, because we are not constrained by a clock. the acquisition is in the analog domain, so it happens at time precision of microsecond. And we have an exposure per pixel, which means that each single pixel can adapt the exposure time according to the lighting conditions, leading to a very wide dynamic range. Three conditions which are very well suited for machine vision and machine learning type of applications. So to highlight the efficiency of the sensor, of course, we can, I showed this video where on the left side you see a regular acquisition done by a regular frame-based sensor. Of course, here what actually appears as evident is the fact that we are producing huge amount of data that are useless. For example, the background is in this case is quite dominant and doesn't give us any new information. And our sensor, as you can see on the right side, is is reacting only to the changes and reducing actually the amount of data drastically, right? So for example, in this case, doing some gesture recognition, some eye tracking would be simpler. So there is also an additional benefit we don't see necessarily in this slide is the fact the acquisition becomes also very fast. And as I said, it's time precision of microsecond. But the fact that you combine this data efficiency, this acquisition sparseness with the high time precision enable us actually to perform high-speed machine vision in real time with limited computational power. So again, benefits are in terms of speed, are in terms of efficiency, are in terms of dynamic range, in terms of low power at the system level. In fact, the high time precision combined with the data efficiency, we can demonstrate, simplify greatly the mathematical model for doing certain computer vision and AI tasks, particularly for doing, for example, computer vision tasks that are related to some motion activity, like, for example, computing an optical flow or tracking. What we do at Prophese, as I said, is we develop the sensor, we develop also the software stack. We want to give to our ecosystem of partners and customers all the tools that are necessary to build an entire application. We work also with actually leading player in the ecosystem, like, for example, Sony, which actually announced a few weeks ago the commercial deployment of our latest sensor generation under Sony reference, and this is now available for evaluation also using our development kit that we started releasing already a few weeks ago. So for us, it's been great as a fabless company to work with Sony as a market leader in the space. So it's also a boost of confidence for us and a boost of validation for our technology. Let's talk also a little bit about the applications very briefly. You can also see some demos in our booth. What we excel at doing with our technology is about particle counting and also particle size monitoring, for example. It's a kind of straightforward with our technology in the sense that naturally you only get the dynamic information, so the motion. So you can actually very quickly do some scene segmentation and do a very accurate tracking, because basically the particle, as soon as it moves from one pixel to the adjacent, you don't need anymore to wait for the next frame. You get from the pixel asynchronously this new event, and you can basically update your tracking model locally, and this gives actually to your tracking algorithm much more robustness and precision against, for example, occlusion. So in this case, we can go up to 500,000 pixels per second in terms of speed and with a greater accuracy. Vibration monitoring is also a very peculiar use case for an event-based sensor, in the sense that it's very difficult to process this type of application with a frame-based camera, also because your frame rate is never really tuned to the vibration of what you're looking at, for example. Any machine is vibrating because there is some motion, and each single pixel in our case becomes a vibration point, a vibration measurement point. So with an HD sensor, you get 1 million vibration measurement points for both amplitude and frequency. And why this is relevant? Because you can then monitor this vibration frequency and amplitude in real time, and you can do some predictive maintenance, because typically change in vibration are one of the first indications for a possible failure mode. So you can do some maintenance and reduce downtime. And yeah, one more example is pattern monitoring. In this case, we play a lot with speed and dynamic range. It's about laser welding. In this case, the video is slowed down several thousand times, but it's to show that we can actually detect and size the particle of the spatter that has been projected by the laser light on a metal surface, for example. And why this is interesting is because you want, for example, monitor this pattern, and from this pattern you can infer about the quality of the welding, and then you do some close feedback loop control on the speed or the intensity of the laser. So very unique application, because also lighting conditions are also very challenging, as you can imagine. So this is another example, but many other are currently being deployed and experimented by our customers. So if you want to know more, of course, don't hesitate to come to visit us in our booth. Thank you.